So section 4.4 is really designed just to get you introduced to the basic idea of coordinate systems. So they don't dive too deeply into hefty computations here. There's several, well, 2 or 3 types of homework questions. So one of the things they'll do is just give you a basis. So here I have a basis, which is, these are 3 linearly independent vectors in R3. So this is a basis for R3, a known vector space. And they might just say, give you some coordinates in the B basis, like 2, -1, 0, and just say what is that in standard coordinates, which they'll call x. And of course that's not difficult. We've already looked at how to do that in the previous video. You're just taking 2 of the first one, -1 of the second one, plus 0 of the third one. So 2 of 1, 3, 4, 1 of 2, 1, 0, and 0 of that. And that comes out to, let's see if I can do this in my head. That'll be 4. Oh, I subtract. 0, sorry. Erase. 0. 6 -1 is 5. And 8 minus 0 is still 8. 0, 5, 8. So notice basically what we ended up doing here was taking the 3 basis vectors, making them into a matrix. I didn't actually write it in matrix form here, but you can, and then times coordinates in the B system, and that produces just your regular x coordinates in standard. So they'll ask you to go that direction. They will also, so that's one type of problem they'll do, is give you some basis coordinates, ask you what the standard coordinates would be for that same thing. A second type of problem, of course, is when they go the other way around and say 6, 8, 10 in standard coordinates is what in the coordinates of this particular basis. And there, of course, you're looking for something times 1, 3, 4 plus something else times 2, 1, 0 plus something yet else times 3, 4, 5 to produce 6, 8, 10, or to write it in matrix form, which I didn't do last time. Solving that. And we have 2 ways to go about this. You can either augment and row reduce, like I did in the last video. If you'd rather find the inverse for some reason, you can definitely left multiply both sides of this equation by the inverse. And that would also get you there. Either one of those would solve you for these particular coordinates. I just happened to give myself a softball example because 6, 8, 10 is 2 times the third vector, so this will end up being 0, 0, 2. But in general, if you can't eyeball the solution, then you either row reduce or inverse matrix for it. So those are two of the types of problems that you will get on the homework. And there's just a couple more things that I need to point out to you. So far we've been doing examples where the vector space is like R2 or R3, or R5 would be similar. It doesn't have to be, so let's consider another vector space like P2, which is all polynomials, in case you don't remember, all polynomials of degree 2 or less. So anything ax squared plus bx plus c, where a and b and c are all allowed to be 0 if you want, and otherwise you don't have the 0 vector in there. So polynomials, second degree or first degree or 0 degree polynomials. So let's look at one particular coordinate system. For this, you could have the polynomial x squared plus 1 as one of yours, and the polynomial 2x plus 2 as another one, and the polynomial 3x squared plus 5x as your third one. I'll claim this is a basis for P2. In other words, I could do some multiple of the first polynomial plus some multiple of the second polynomial plus some multiple of the third polynomial and produce any second degree or less polynomial that I so desire. In other words, it spans all of P2. In case that's hard to see, it's easier maybe to think of this same basis as vertically written vectors, where you've got the x squared coefficient, the x coefficient, and the constant coefficient. So this first one would be 1, 0, 1. The second one is 0, 2, 2. And the third one is 3, 5, 0. And as long as you keep track in your brain of the fact that the top coordinate here, top number, is the x squared coefficient, and the middle number is the x coefficient, and the bottom number is the constant, then you're fine. You're working with exactly the same information here as you are here. Which, by the way, since these are linearly independent as well, this is both a representation of that, but it's also happens to be a basis for R3. It's 3 linearly independent vectors from R3. Which leads me to introduce a new word to you. Isomorphism. There's a word that you can impress your friends and colleagues with. Your family will think you're so smart when you pull that one out at dinner tonight. So isomorphism, iso just means same. And morphism, morph means shape. But mathematically, an isomorphism are two different things that can be mapped directly to each other. Any operations on one are exactly the same as doing operations on the other one. So here we would say that P2 is an isomorphism of R3. They both have vectors with 3 components. And anything in P2, if you write down 6x squared plus 5x plus 4, there's an equivalent vector in R3 that matches that, right? Obviously 6, 5, 4. We'll use the language of isomorphism a little bit in tonight's homework. It's in the true and false, just as a hint. And we'll continue to use it occasionally throughout the rest of the course. And if you go on to further math courses, you'll definitely hear about isomorphisms a lot. Okay, so we'll look at a couple examples in the next video, and then you'll be ready for the homework.